All right, well, let's take a look at this. This is section 3.2, and what we're going to be doing here is just adding on to the big picture idea, which is in 3.1, we talked about how a researcher, if they could, you know, when studying a population, go and talk and survey every single person in the population. But because that's not feasible, you can't go and survey millions of people. Plan B is to just work off of a sample. Well, the samples, what we also talked about was how they only give you best guesses. And there's a pretty good chance that if you do just one sample, it as far as a guess, it could be off. It could be a little too high, could be a little too low. So when you do a sample, the other thing that you should do is also create what's known as a confidence interval. So what that's doing is letting your audience know that, hey, when I did a sample, this is the initial best guess that I got, but because it could be off, I'm going to let you know how far off it might be. That the actual parameter might be this much higher, this much lower, but it's somewhere in between here and here. So to get us started right away with an example, they did a study. This was in 2011, and it was asking individuals, were they getting health insurance from their employer? Again, it was only based off of a sample, pretty good size sample, 147,000 individuals who they talked to. And when they talked to these adults, what they found out was that 45% of them said that they were getting their health insurance from their employer. And so because that was based off of a sample, we would say that it's p hat equal to 45%. Remember, p hat signifying that it was this 45% was based off of just a sample. Now, again, that would be what they call the initial guess. That maybe it's 45% of all of these American adults. Maybe it's 45% that are getting their insurance from their health employer. But because it's based off a sample, it could be off. And so now what we're going to do is introduce something known as a margin of error. And what the margin of error is going to help us do is to widen it out so that it's not just one particular value, but it stretches it out to say, hey, the truth of what we're trying to measure could be maybe a little bit lower, maybe a little bit higher. But these are known as interval estimates. Interval estimates. And what they also are described as being the range of plausible values, or another word is reasonable. Like from where to where is most likely to be the truth about the population. And the way that you widen out from not just being a one value answer, but now you have these two values that go from left to right or from low to high, and that's this right here. It's known as the margin of error. And in this particular study, they said that they know that, yeah, that 45% was just really a best guess and probably not a bad guess, and said it was a pretty big sample and it was also a random sample. But still, they're being very transparent and they're saying we could be off by plus or minus 1%. So what they do is they say, well, the plus minus 1% would mean that it could be the truth about how many people are getting their health insurance from their employer could be as low as 44% or maybe as high as 46%. So again, it's just widening it out. But that right there is still a very, very narrow interval. So that's not a bad, like, tight little window of where the truth could be. But at the same time, what this is telling us is that, what other things don't make sense? To say that 50%, no, because it's only something from 44 to 46. Or could it be 40%? Probably not. The interval saying that it's as low as maybe 44. So this is what we're going to be doing today. Is just introducing these confidence intervals, and sometimes we're going to be using what's known as margin of error, and that's just in terms of abbreviating just ME. But one of the biggest things that also helps with these intervals is that if the margin of error is smaller, then that window of where we are saying as low as this to as high as that is going to be much smaller and give us more of an accurate, like tight little window. Now, you might remember we also talked last time in 3.1 that if you use larger sample sizes, that's one way for you to shrink down, right? Like narrow in on like the bullseye of what it is that you're trying to measure. But let's look at some other examples where in each of these, like even here with example 2, they're going to give you the initial point estimate, but then they're going to say that since that was really just at best a guess, how far off they might be. Now, this one here is about averages. It says they did a sample of 755 US cell phone users, and they found out that the average number of text messages that either were sent or received was 41.5. So that's their initial, like their initial guess, maybe 41.5. But then they're being transparent and they're saying, hey, we could be off. It might be 12.2 points higher than that, or maybe lower than that. And so what we're always going to do is we're going to zone in on that initial value. And that's what A is all about. A is saying identify the statistic. And remember, whenever we see the word statistic, that's also a way of saying what did the sample say. And according to the sample, is that it was 41.5 messages that are being sent or received on average. As for our notation, it would be X bar. And X bar is a notation for saying that's the mean based on just the sample. And then now we're going to do the widening it out, right? Although 41.5 is their initial guess, they're off the truth of about how many text messages are being sent and received per day. Might actually be 12.2 points lower than that, or it actually might be 12.2 points higher. So you would do both of these two things in your calculator. I would say start with the minus version first so that you can get your low amount. That's going to get you to 29.3. That's the low. And then you'll write the second value whenever you do the plus version as the high value. But when you do your answers, always write it like this. Write it from the low to the high. And so now we've stretched it out. How many text messages are sent or received per day? Maybe it could be as low as 29.3. Maybe it could be as high as 53. But then that's where the interval stops. Anything in between there also could maybe be the truth. Could be like 30, could be 50. But something like 60, no, probably not. Something like 10, no, probably not. And then that's where this sort of like little question is going to come up. It says, based on the interval, this is part C, would an average of 50 messages be plausible or likely to be the truth based on this interval? And yeah, because 50 is one of the values in between here. Again, that's what this interval is saying. It could be anything from like 29 all the way up to 53. When we think about the actual population of all people who are sending and receiving text messages, 50 is in between there. So it could maybe be 50. And so short answer, we'll say yes, an average of 50 for all people does make sense. Explanation, because 50, you can use other words, but I'm going to use the word contained, or it's within the interval. But if that changed that question to be, is 60 a plausible value? You would say no, because 60 is on the outside. And we'll do some of those. We'll do some where sometimes, it's they're asking about something that's inside, something that's on the outside. Let's try another one. This one about adopting a child in the US. Now, one of the things you're always going to want to ask yourself first, is this study about a proportion or is this study about a mean? Take a few seconds just to read this new example 3. And then for yourself, judge, is this about an average, mean, or is this about a proportion? And for us, there's always going to be one thing that triggers for sure that this is about a proportion, and that's because of the percentage. This is a proportion study. 44% out of the people who they surveyed said that it is too hard to adopt a child in the US. So that would be your statistic because it was based on a survey or just a sample of individuals. They didn't survey every single American adult. So for A, you would put what's the best estimate? 44%. That's what the sample said might be the truth. Maybe it's 44%. But again, that could be off. Again, anytime you use a sample, it's never going to be an exact, it's never going to be exactly what the population is. It's going to be, hopefully close to what the truth is. And then you'll see there, the last little part of that prompt says that the margin of error was 3%, which is them being transparent. It might actually be 3% higher, 3% lower than their initial point estimate. So all you would do with this is do 44, take away 3, 44, add 3, or more simply, the proportion of people or the percentage of people who say that it's too hard to adopt in the United States is something between 41 to 47%. That's the range of plausible. Like it could be 42, might be 43, could be 44, 45, 46, 47. But then once you get outside of the interval, no, probably not 48, probably not 49, probably not 50. Again, our confidence lies within the interval. So the last little part here is saying, is it plausible or is it reasonable that the percentage of people who say it's too hard to adopt in the US is 50%? And you would say no, because the highest at the interval saying that it might be is 47%, not 48, not 49, not 50, or anything higher than that. So short answer would be no. And as far as your explanation, just keep it real short and sweet when you're doing the homework. You can say no because 50% or 0.5 is not in the interval. Or you could say no because the proportion is at most 47%. It's not contained or within. So it's not plausible. It's not a reasonable estimate for the population. All right, let's try something else. Now, when I say let's try something else, it's actually something that we have seen before when we were doing standard deviation. We were using standard deviation to help construct or calculate a 95% interval. And that is coming back, except the only thing is now it's not your mean plus minus 2 times your standard deviation. It's the statistic. And the statistic is going to be the center where your best estimate is, plus minus 2 times standard error. Remember it showed up last time. Standard error is whenever you are measuring how different or how similar samples are. So it's not just one sample with people in that one sample. It's many samples. So that's coming back. And what this is known as is doing a 95% interval. Like it's specifically used for that. Whenever you want to calculate a 95% interval, or for short, you can just put CI. And so you do that calculation, and the 95%, what that's going to be is a way of indicating like how confident you are. We call it the level of confidence. And we're going to look at a few of these throughout the course, which is maybe you're 90% confidence, maybe you're 95, or you're like super confident, like 99%. But for today, we're going to see the 95. And if you're ever wondering, like, well, where'd the 95 come from? It's the idea that if they were to do a study, like let's say 100 times to try to measure what the average for something is or what the proportion is, if they were to do it 100 times, 95 of those times you would get something that agrees with your value being somewhere in this, between this interval. Now, the main thing I want you to be thinking about is these intervals are trying to capture um, what the truth is about the population. So you can use the word capture, or again, I'm going to be using more like the word contain, like it's contained within here, within these two values. Now, this page here, it's not going to end up being something that you find yourself doing like on the homework, but it's mainly to try to address the conceptual idea between about what a 95% interval is. So here's an example. When it comes to movies, Hollywood movies, and how much it cost budget wise for them to make these movies, somebody actually got a list of all the movies in 2011, just as an example, and they calculated what actually was the average budget. So we use mu, the average for all the movies in that year was a little bit over 53 million. And that's the truth, right? There's no guess here. Like, that's actually really what it was. Now, what we're going to do is we're going to look at how, if somebody was to have done many of these samples, you can see that some of them may have been too high of an estimate, like these over here. These are samples that are guessing that it might be about 80 million average to make a movie in Hollywood. No, that's way too high. It's actually truthfully only about 53. And then some of these are guessing only about 30 million. So they're guessing way too low. Now, what's going to happen here is we're going to take the idea that there could be three different samples that are all three making a guess, but they might be off. But some of them are not so bad at guesses as some other ones, because when you do an interval around each of these statistics, some of them at least contain the truth. And then there might be one or more that it's just way off, that even if you do an interval around it, it completely misses what the truth is all about, which is the 53 million. Now, we're going to be using this here in just a moment. That's the standard error, which is if these are a bunch of samples, that is how much they deviate from each other. Like, that's how much variation there is. Now, to get back to this idea, like, okay, what do you mean that there's going to be some samples that are such bad guesses that they completely miss like the truth about this whole idea of the average budget? So let's do this. Let's maybe go like right about, I don't know, maybe let's just go right about here and do what this sort of our 95% interval. Like, these right here are guesses that are pretty close to the center, and so they're not that bad of a guess. They were maybe not exactly close to the 53 million like truth, but they weren't bad. They're still relatively close to it. And so one of those guesses that's showing up on that little number line could have been like an estimate of like 40, which is right there. And it's not too crazy off. I mean, it is 13 million too low of a guess. But when we say that it's not like the most terrible guesses at what the budget is that if you were to take the 40 as your statistic and build an interval around it with the standard error, which they provided for us was that 10.2, and go ahead and put this into your calculator. And again, do the minus version first so that you can write it from low to high. Now, if I was the voice for this little sample, this guy right here who's like, hey, I think the budget on average is 40 million, but I could be off. It might be actually something a little bit lower than that, or something maybe a little bit higher than that. Could be as low as, and here's what the calculator would get you: 19.6 and 60.4. So that little sample, I mean, if it's being really honest, would say my initial guess is about 40 million, but I could be off. It might be something as low as 19.6 million to as high as maybe 60 million. And it's not lying. Because remember, the truth is 53 million. So for it to say that it's something as maybe as high as 60 million, that at least does contain the truth, which is that it was really 53 million. So again, that's what we mean that it's not the most terrible guess. I mean, it was low, but at least the interval around it is saying the truth. Yeah, it's something between 19 and 60. If you look at the next one, part B, one of the samples was guessing about 70 million. You can see that also is still kind of relatively close to like the center. And if you do the same thing for this one, the statistic, treat it like the center of your interval and repeat with the minus 2 times standard error plus 2 times standard error. And then you put your little calculations right here. Go ahead and do those, right? And while you're doing those, I'll make a few little comments, which is that if I was the little voice for this statistic and said, hey, my guess is that it might be about 70 million, but I could be off. It's maybe the average budget is maybe something as low as 49.6 million or as high as like 90.4, or it's something in between there. And that's still accurate, right? The actual true budget of 53 million is somewhere in between 49 and 60. So this would also be one that captures the truth, the real truth that it's 53 million. But if you look at the last one, suppose one of the samples was like, hey, I think it might be like 84 million. Notice that that's way out on the tail. So it's guessing way too high. It's guessing like 27 million, almost, I guess, close to like 30 million, like too high. And so it's such a bad guess that whenever you do a confidence interval around it, you'll see that it completely misses the mark and does not even include the truth, which is the 53 million. You would repeat with the minus 2 times 10.2 plus 2 times 10.2, and you'll get 63.6 to 104.4. So that little statistic would be saying, hey, I think the average budget might be about 84 million, but I could be wrong. It could be something in between like 63 and 104. And nope, that's not actually what the truth is. So it was such a bad guess that its interval doesn't even contain the truth. But the whole 95% idea is that these 95 percentage wise would all be samples that agree with the truth being somewhere between like here and here. Like there would be 95 of them that at least would contain the truth. This last one would be a little no. All right, let's try something else, which is also really huge, right? What we're about to look at here is a very important thing. In statistics, often one of the most interesting things to check is to see whether an average or whether a proportion differs when you look at two different groups. Right. So we're going to look at, there's going to be a lot of times throughout this class when we're going to be checking to see whether something about group one is different from group two. Now, one of the classic group one versus group two combinations is like male versus female, or you could do like younger versus older, or people who are employed versus those who aren't employed, or going to school full time versus part time. A lot of ways you can do it. And these are going to be some of like the main heavy hitters we focus on, whether they differ with respect to like their averages or maybe with respect to their proportions. And so we know about X bar and mu, but now if you're doing two groups and you want to see whether there's a difference between the groups, you would have to do the average for the first group and the average for the second group, and then subtract them to see whether one of the groups is higher than the other. Now, the X bars are mainly just to say you're working with a sample. The mu's would be if you're still wanting to make some sort of guess about the larger population of everybody in group one and everybody in group two. If that's what you wanted to know, but you couldn't actually go talk to everyone, then you would just rely on samples to see what they suggest might be true, whether there's a difference between the groups or not. Same thing for proportions. If you wanted to know something about the proportion of everybody in group one versus everybody in group two, but there's just way too many people and you can't go survey all of them, then just do proportion one for the first group and proportion two, and then subtract those. So you would have like a best guess for group one and a best guess for group two, and then you would subtract them. And as long as you don't get zero whenever you subtract them, that would suggest that there is some sort of difference between the groups. And that's what I want to look at here. Just a quick little like exercise about whenever you're calculating, it might be just one group, might be two groups, could be proportions, could be means. But then this is a big one. When you're calculating your lower and your upper value, it could be sometimes where they give you the margin of error, and it could be sometimes where they give you the standard error. And margins of error, notice when you look at the two formulas, you do not need to do margin of error times 2. Standard error is like standard deviation, where it takes 2 deviations to get to the left and to the right to get the complete 95%. But margins of errors, they're already doubled, right? So I'm gonna think about it this way. I'm gonna draw the picture. You don't have to necessarily do it, but if you were doing your center, this would be, that would be 2 standard deviations to the left and 2 standard deviations to the right. So you would need to double it, take 2 to the left, 2 to the right. But margins of errors, I'll just use the same graph. Margin of error is already just one of those margin of error to the left and one margin of error to get to the right. So it's already twice the size. So when you look at A, B, and C here, that's all they want us to do is just to calculate the lower and the upper. But for the first two, it's got standard error. So these would be when you take the statistic and you do your minus and you do your plus, you have to do times 2 to get all the way to the complete edge of the 95% interval. In other words, you take your statistic, and this one it's a proportion. You do your minus, your plus. But to get the complete 95% interval where it starts and stops, you would need to do times 2. So go ahead and do the calculations. Just, again, remember off to the side, somewhere put what was the low value up to the high value. I'll let you do that. And then for B, same thing, except it's about an average, but no different. You would take the statistic, whatever value they got for the best estimate, and likewise, if it's standard error, you have to double it. You would write your lower to your upper value. Now, again, I'm leaving those for you to do. I'll fill them in just a moment. But for C is the only one that's margin of error. And so that'd be the one that whenever you get your statistic, and they've already did it, they said that was a group 1 and a group 2, proportion-wise, and the difference was 0.05. That'd be your statistic. But this one, no, you don't need to do times 2, because this time they gave you the margin of error, which is already like doubled, already twice the size of a standard error. It already reaches to the very edge of the 95% interval. Again, that would just be a calculator thing. But that one's actually Pretty straightforward, 0.03 and 0.07. And the other ones, if you haven't done them already, or maybe you haven't, just to double check that we're in the same page, 0.64 to 0.80, 20.6 to 33.4. Now, before we go on, there is one more thing that's missing. These little intervals, all three of these intervals were based off of information that they got from just the sample. But we never want to lose track of like the big picture. The reason why all three of these A, B, and C would have maybe just used samples is because they would not have been able to maybe go and talk to the millions of people who they were wanting to do a study about. So, but that was what that would have been their ultimate goal. So, in the first one, if they only did a sample or a p hat, it was in order to say something about the proportion of all. Here, I'll put it, I'm going to put it way over here on the outside. The notation for the parameter, which again would have been respect with the idea that they're trying to make some sort of assessment about all the people proportion wise, would have been proportion from the sample, trying to say something about the proportion of everybody in the population. And then over here, I just put a little circle around the X bar. That was a mean from a sample, but that sample would have been trying to give us something to say about the population, the average for the entire population, or the mute. And then this last one would have been, well, they did a sample for proportion 1, they did a sample proportion 2, and they subtracted them. But that the intent of that would have been to try to be able to say whether there's a difference for the proportion of everybody in group 1 versus the proportion of everybody in group 2. So those would be the parameter notations or the population notations. All right. Now, one of the other very, very, very important things is there's going to be a time where they ask us to interpret, like putting a conclusion to studies, and what did they discover? What did they find out? How confident are they in their result? So it'll be that we're asked to do interpretations of intervals. And when you write these, I went ahead and put a template for you. And this is what I want you to use. There is very detailed information that needs to be included in each of these interpretations. And that's going to be how confident they are, like the level, which is today we're going to be doing 95%. Whether it was about a proportion, whether it was about a mean, whether it was about a difference of two groups. Then you also want to mention, what was the variable, who were the cases, and then from where to where is the plausible range for whatever it is that they were trying to measure. So I went ahead and just already have ready for us an example where we can do exactly that. Write an interpretation for the interval. So if all we were doing is just looking at those numbers there, we can see 9,600 and we can see 13,600, but we want to write about what that meant. And it's actually all there. The purpose of those two numbers was to tell the scientists what was the mean amount of carbon per square kilometer. That would be the variable. For what or for who? For tropical forests. And not just some of them. It was meant to try to say something about, in general, about all tropical forests. And it's that much. It's about that many tons. So the interpretations are always going to start something like this. We are 95% confident. And notice that all I'm really doing is just following this template up here. We're 95% confident And of those three, right now we're doing a mean. This is a study about the average amount of carbon. Confident, the, and you don't have to put the word true. I mean, that's not a bad word to use, but that the mean, then we're just really going to use the words that they have in the prompt. That the mean amount of carbon per square kilometer for all. Now we're going to mention the cases. In this, they were studying tropical forests. Tropical forest. Now, the word all is optional, but I don't think it's a bad word to use. Like, because this is trying to do something referring back to the population. Now, if you're looking here, yeah, they only did a sample of inventory plots of tropical forests. But again, they would have liked to gone and measured every single tropical forest. They just can't do that. But that is what this conclusion is about. That for all tropical forests, that the amount of carbon is something between 9,600 and 13,600 tons. But this is something I came up with just to try to help my students. You know, is there specific stuff that you have to have in the interpretation? Yeah, and that's why I gave you a little template. That's something that you would want to have on your reference sheet whenever we get to the test for this unit. That way you can make sure you have a nice detailed sentence with all the goodies in it. But here, we're going to try another one. In this one here, they give us the study. Go ahead and read the prompt just to give yourself a quick little boost of what the study was even about, who they were talking to, what the variable was. And note that it talks only about a sample. But truthfully, if they had the time, the resources, the money, all that, they would have gone and talked to every single person. But there's just way too many people to go talk to. So plan B, let's just see what a sample tells us. And hopefully it gives us a pretty good estimate. All right. So the other thing to ask yourself, is this about average, or is this a study that they were trying to calculate a proportion? And they don't ever say, notice that they don't ever say average. And that's one of my little tips. Anytime it's a study that's doing an average, it's going to say average or it's going to say mean. But in this one, the giveaway is that it's is a percentage there. They found out that 31% of the Americans who they talked to said that the economy should be a top priority. And this one, you don't need to do any calculating. It's already done. The sample led to an estimate of about 31%, or it actually might be better for us to go and turn that to a decimal. Because if you happen to notice the margin of error, it's not a percent. It's just a regular plain old decimal. So for that reason, whenever you're doing the homework, wherever you see a problem where they're both percentages, great. Go ahead and do whatever you need to do with them. If they're both decimals, great. Go ahead and do whatever you need to do. But if one's a percent and one's a decimal, I'd recommend changing them just both to decimals. That way, when they ask us to calculate the confidence interval, we take that statistic, which is this is it. All right, this is the statistic, the 0.31. And notice that since it's margin of error, we're going to do a minus version, we're going to do a plus version, but you don't need to do times two. Okay, let's see. I'm going to go and just fit it right in here. You take your statistic, do a minus version, do a plus version, get your low to your high. Go ahead and do it. Go ahead and do those calculations. Calculator if you need it. And that's going to give us the range of what percentage or what proportion of people, whenever they did the study, felt that the economy should be a top priority. You should get 0.27 to 0.35. And you're more than welcome to just leave it as a decimal. And maybe I'll do that on this one, and maybe for the last problem that we do, I'll just show the flexibility. If you want to make it 27%, 35%, maybe I'll do it on the next problem. But since this is only the second confidence interval that we've written, I'll go ahead and take the lead on this. When you write the interpretation of what they discovered, the template says, start off with the level. How confident are they? Well, 95% confident. And what is the thing that they were trying to measure? The proportion. Or you can put the word percentage of, and then who were they trying to say something about? The proportion of all Americans. And then what about them? What's the variable? Who say the economy is or should be a top priority? And then from where to where is the truth? It's a value somewhere between 0.27 and 0.35. So either 0.27 or 0.35 or something in between there. Anything else on the outside, like 0.40, no. And that's what the last little part of this one here is to end this problem is for D. It says, would it be plausible that the actual truth is that less than 25% of people say that the economy should be a top priority? And according to this, no. The lowest that it might be is 27%. So what you would do for this one is just short answer no, and then give a reason why. I mean, some students want to say, 25% is not in there, but I think it's not just that 25% is not in there, 24% is not in there, 23% is not in there. Anything less than 25% is not in the interval. So maybe one way we can just knock out the explanation is to say that no, something less than 25% doesn't make sense. And the reason why is because the interval suggests the actual true percentage of everybody who says that the economy should be a top priority is the smallest it could be, or it's at least 27%, but nothing smaller than that. According to the interval, it's 95% sure that the smallest it might be is 27%. So anything less than 25% doesn't make sense. All right, now I'm going to leave that on the screen there just in case anybody's still writing up these last little notes. And there's just one more example that I want to do before we call this lesson done. And it's mainly because I want to do one where it includes two different groups that are being compared. And again, one of the classic comparisons that's done in a lot of studies is whether there's a difference between male and female. Like, does gender matter? Does sex matter? So in this one, it was about males and females. The variable, you can see it there. It's in that second sentence. Whether they agreed or disagreed that for every one person that there's one true love for you, like waiting out there in the world. You just got to find them. Right. So, and you can see also the statistics are there, which is based on the sample of men. You can see their fraction, how many of the men agreed. And here I'll underline it. This is for the men, for the males. How many out of 12, 13 said that they agreed? Then for the females, you can see their fraction. So since those are both samples, those are statistics. And so I have it in bold there, which is we want to see whether there's a difference. And when you get to part A and to part B, that's where the notation is going to come up. And so since these are both proportions, we're going to be using P's. Now, remember, we have sometimes P's with hats and sometimes P's without. Whenever you're doing P's with hats, that's whenever you're actually referring to the sample or to the statistic. And I also went ahead and gave a little bit of, I mean, it does the order matter? I mean, there can be some times where I go ahead and just give you a little bit of nudge, and right here I'm saying it, males minus female. But if you're wondering, like, why did we skip part A? Part A is just the notation, but we already used p hats for part B because part B is talking about the sample, the statistic. Part A is saying, well, what would the notation be if you were doing it based on the parameter, which is the population? And it would be that whether there's a difference between the proportion of all males versus all females. And if we don't put the hat, that's the idea that it's about all of the population. But let's go to do B. And what B wants us to do is actually calculate it, which again, that's what we have up underlined up there. That was 372 out of 1213 for the males. And that was 363 females out of 1412. And you can go ahead and just put that in your calculator. And what you should get, double check for yourself that you get 0.05. Now, both of these were the samples, like sample one, sample two, but this right here is what we're going to say is the statistic, which is there was a difference. Now, you might even put a little note here, which based on the way that we subtracted, we did male minus female, and we got a positive value, which would suggest that male must have been higher. Now, if you've got some room, I don't think it's a bad idea. Maybe right here you could put 0.307 and 0.257. Those are the decimal versions. That's just another a quick way for me to show you that, yeah, male was about 30% who said there's one true love for everybody. And the females were only about, 25, 26%. So lower than males. How much lower or how much higher was male? About 5%. Now, once you have the statistic, that and you also have either the margin error, standard error, and this one here it is. This is the standard error, or this was 0.018. And if you're wondering, wait, where did the standard error come from? We will, when we get to a little bit more into chapter 3, actually go ahead and show how we can get standard error using stat key. But for now, they're just giving it to us. When we get even further into the class, we'll introduce a formula to be able to get standard error on our own. But let's go ahead and do this. You would take your statistic, and remember, whenever it is standard error, you do need to double it to be able to get your accurate lower bound to your higher bound. And you should get 0.014 and 0.086. But again, with your calculator, it's always important right now that while we're going through lectures to try the calculator stuff on your own. I mean, you're going to get to practice with it with the homework, but still just to make sure that, hey, your calculator is doing what it needs to do, or maybe you have still kind of a freshly new calculator that you're getting more comfortable with how it functions. And I'm just starting off with the the same little template. They want us to interpret that interval. And we can say that we are 95% confident. Again, remember, it's not going to end up being any kind of question that shows up, but the 95% would be that if they did 100 samples, 95% of them would agree about where the truth concerning the population is. So we're 95% confident that the difference, and all I'm really doing here is just using their words. They've got it up there. The whole purpose of this interval was to do the difference between the proportion of male and females that agree. And I think that's not a bad idea. It's just, if they already have the words there, it's totally okay to just use their words. There's even times where I've tried to paraphrase what the whole study was about or what the intent of the interval was. And I was like, you know what? I feel like I'm cutting out important stuff whenever I try to paraphrase it too much. So it's better just to go ahead and just put it all in there. It was a difference in proportions. It was about male and female. The variable was about who say there is one true love, and then give the interval. The difference is somewhere between, and this one I'll go ahead and do the percentages. I mean, you can leave it as decimals if you want, but it would be 1.4% and 8.6%. Now, the last little thing here, and we'll be done, is remember that the initial samples were saying that male was higher by 5%. Well, all that's happened here is it's been extended. It's been widened, that the males might be higher by about 1.4% or even as high as 8.6, almost like 9% higher than female, who say that yes, there's one true love for every person out there. But what this last little part is going to ask you is, hey, is no difference, that there's no difference between the groups, a plausible thing, or is that reasonable based on the interval? And what I've told my students to do is whenever these questions come up about no difference, is to be very specific about what number that is suggesting, which would be zero. And so another way you can rethink about what this last little part is asking us is zero in the interval? Like, is zero difference in the interval? And no, right? The interval is saying that male is higher by either 1.4% or even as much as 8.6%. Yeah, let me make sure I don't write this a little too weird. Yeah, that's 8. Sorry if that was like too confusing. So keep it short, like no would be the short answer, since zero is not contained, or you could say within the interval. Or you could even say the CI, but I'm just going to go to it right. It's not within um, the interval estimate. In other words, there's more likely to make sense to say that according to the interval that there is a difference. Even more specifically, that males tend to say more often that there's one true love out there as opposed to female. All right, so another really good lesson in that it's starting to just really peel back what the whole idea of statistics is all about. Yeah, we want to be able to say things about the entire, like all of the population, but since it's not possible to always go and survey everybody, we're having to leverage smaller samples, and hopefully those samples are really good samples. By unbiased random samples would be the best thing. and that they're at least hopefully giving us pretty good estimates or at least a pretty good idea of what the truth is about populations. But I'm going to go ahead and end the recording there. This lesson didn't have any stat key in it, but I'll see y'all on the next lesson. Have a good one.